Today we're going to take a look at the mole and molar mass in our compounds. So counting atoms, ions, or even like molecules would be absolutely impossible when we count with a regular number, because if you are looking at a grain of salt, for instance, there are billions, trillions of each atom present from Na and Cl. So because we have to count such big numbers of atoms or particles to be able to make sense of what we're seeing in this world, we have a new counting number, the mole. So we know in counting, a pair means 2, a dozen means 12. And what we know is that a mole is equal to an exact number as well. It's just a really big number. All right. So 1 mole was defined by using a specific isotope of carbon, carbon-12. They said 12 grams of carbon-12 has 1 mole, or represents 1 mole of compound. I don't know how they got that number, but they did it. So the number for a mole, what 1 mole represents, is 6.022 times 10 to the 23 of that substance. So what 6.022 times 10 to the 23 looks like is this number that I wrote below. Okay, the 23 tells me I need to move the decimal 23 times from where it currently is this way. So 23 places and fill in the rest with zeros. This number is massive, and this represents the number of particles or atoms of a compound present in 1 mole. So when I say 1 mole, I'm not talking about 1 particle. I am talking about lots of them, but we often use the word mole to help describe that. This number is called Avogadro's number. Avogadro's number. Different than avocado's number. Avogadro was the person who came up with this thought. So when I am measuring the mass of a compound, we always refer back to what is the molar mass or the atomic mass of a compound. And that comes from the atomic mass of each element. If we look at the atomic mass of each element on our periodic table, that is technically the molar mass, or the number of grams that 1 mole of that substance represents. Okay, so the molar mass of a substance refers to the mass of 1 mole, or this many, of that compound or ion or element. All right, when we are looking to calculate molar mass, then we're going to use the atomic mass of those elements. Atomic mass and molar mass mean more or less the same thing. Okay, so we're going to use those atomic masses. All right, so when we look at the atomic mass of sodium on our periodic table, we find the element sodium, okay, Na, it's element number 11, and you look at the atomic mass for sodium. It's right underneath its name on our periodic table. Right now, I want you to take out your periodic table and find the atomic mass of sodium. Pause the video and then unpause to see if you got it right. The molar mass of sodium is 22.99 grams per mole. The unit grams per mole tells me that 1 mole of sodium weighs 22.99 grams on my scale. We're going to do the same thing for oxygen, but when we have a name for a compound or an element, we have to turn it into a symbol or a formula, just in case. Because what we know about oxygen is that it is part of P.S. Brinkelhoff, or it's diatomic. So when we talk about the molar mass of oxygen, I'm not talking about the molar mass of 1 atom of oxygen. I'm actually talking about oxygen as we experience it in its common form on Earth. So here, when I look at this formula, there are 2 atoms of oxygen in that formula. Therefore, when I go to calculate its molar mass, I have to consider that the molar mass, which is the symbol big M, the molar mass of oxygen is equal to the molar mass of an oxygen atom times 2, because there's 2 of them present. All right, so when I'm looking this up on my periodic table, we're going to times the molar mass that we find for oxygen by 2 to account for the fact there's 2 in this molecule. So the molar mass of oxygen is 16.00 grams per mole. And note that I'm using units in all of my calculations. And when I multiply 2 by 16, I'm going to get 32 grams per mole. And we're going to talk about numbers and counting these numbers later, but because there's 2 decimal places for every atomic mass or molar mass on our periodic table, we're always going to report our molar mass to 2 decimal places. And it will always get the units grams per mole. So we're going to do that for maybe a more complex, if you will, atom. All right. In our compound here, okay, CH2O, we have 3 different elements. Therefore, we need to use the molar mass of each of those elements to come up with the molar mass of our entire compound. So let's count the number of each element here. To get the molar mass of our entire compound, so CH2O, I need to find the molar mass of each of those elements. I need the molar mass of carbon. And because in my formula there's only 1 carbon, I would technically multiply this by 1 or just add it from our normal count. I then need to add the molar mass of our next element, which is hydrogen. In our formula here, though, there are 2 hydrogens in our compound. So we have to multiply the number, the molar mass that we get for hydrogen on our periodic table by 2. Okay, to account for the fact that there are 2 hydrogens in this molecule. And we're going to do this one more time for the molar mass of oxygen. Oxygen, of course, there is only 1 here, so I need to multiply that by 1, or just add it as is. Now I want you to pause. I want you to write out your work here. Find the molar mass for each of our atoms, okay? Add them up and multiply appropriately, all right, to see if we come up with the same answer. Pause now and do your work. All right, as we have added this up, we should come to a molar mass of 30.03 grams per mole. All right, let's try sodium iodate. Again, the first step to calculating a molar mass is that you must find the formula first. Because when I look at this, I see sodium, and I might just add the mass of sodium. And I find iodate, and I might incorrectly say, oh, just add the mass of iodine. So iodate is IO3. Okay, and so when we write our formula, we get NaIO3. I want you to pause now and calculate the molar mass using this idea. We need to know which elements are here, how many of each there are, and multiply the molar mass of each element by how many there are in this compound. So, using your periodic table, add this up now and see what you get for the molar mass of sodium iodate. Okay, the molar mass that I got, again, you can always use a little like subscript here to tell me which one you're using, or you can just say like the molar mass is. I got 197.89 grams per mole. Don't forget, if you got it wrong, that you need to multiply the molar mass of oxygen by 3 first. All right, the last one. I want you to try this one on your own. A reminder that we need to multiply by how many atoms there are. So note that we have 2 groups of NO3. Pause the video now and try and calculate the molar mass of calcium nitrate as shown here. Okay, the molar mass that I got for calcium nitrate was 164.10 grams per mole. The way that I got this, I have 1 calcium atom, I have 2 nitrogens, and I have 6 oxygens when I'm adding those up. All right, now that we can do the molar masses, we need to apply that to calculating the number of moles of something. So if I weigh 10 grams of, let's say, table salt, NaCl on the scale, I might want to know how many moles there are present. Remember, if there is a mole, it tells me that there's 6.022 times 10 to the 23 units of NaCl in that 10 grams. Okay, so what we're going to do is we're going to need a formula for this. Our formula for counting the number of moles of a compound is N is equal to little m over big M. Let's define all of those variables. The letter N stands for moles. Okay, so it is the symbol in our equation for moles. The unit here is mole, or MOL, a short form, if you will, of moles. And to calculate the moles, we take little m, which stands for mass, okay? And the mass is always measured in grams of that compound. And we divide it by big M, which we just finished calculating, and that's our molar mass. And a molar mass is measured in grams per mole. Okay. When we solve this equation, when we divide our mass by the molar mass of that compound, we can find out the number of moles, or the number of particles almost, that are there. Let's try it. So note that I'm actually going to use the same compounds as we calculated the molar masses for above. Okay, if we hadn't already calculated the molar mass, that would be one of our first steps to be able to find moles. So determine the number of moles that are contained in 56.42 grams of calcium nitrate. What I like to do is make a list of what I know. I am trying to determine the number of moles, so I am trying to find N. I have 56.42 grams. Now, it's not explicitly stated, but this is a mass because of the unit grams. So I can say I have a mass, okay? And then we need the molar mass of that compound. And to get a molar mass, we would have to calculate it by writing out the formula here. So CaNO3 2. And if you use your remembering brain, we just calculated that molar mass. So I'm going to scroll up and copy the molar mass that we just found. So 164.10 grams per mole. Excellent. Well, the only formula I know to calculate N, or the number of moles, is N is equal to little m over big M. I'm going to write out my formula because it might not always be right above in our notes. What I am trying to find is our question mark here. We are trying to solve for N. And currently in our formula, it is all by itself, so we actually don't need to rearrange our formula. So we're going to sub in what we know. We know that the mass is 56.42 grams, and we're going to divide by the molar mass of 164.10 grams per mole. When we calculate that, okay, we'll punch that into our calculator, and we are going to get that N is equal to 0.3438 moles. Now, why did I choose to round it to that perfectly? Well, again, when we get to physics, we're going to talk all about this. For now, what you need to know is I gave you 4 numbers here, so you should have 4 numbers here. It's not a big deal. We're going to talk about it later, but I will keep it there just in case. All right, let's try it again. We're going to determine the mass of oxygen present when there are 0.315 moles of oxygen. So this time, we are looking to determine the mass. All right, and we are given 0.315 moles. So N is equal to 0.315 moles. Now, a reminder, oxygen is O2, the element, and we calculated that molar mass above. It was 32.00 grams per mole. Now, when I'm trying to decide what formula to use, I need to find a formula that has all 3 of these variables in it, which is exactly the one we wrote above. So I'm going to write N is equal to little m over big M. And I'm going to circle what variable I'm trying to solve for. So in this case, I'm trying to solve for little m, the mass. At this point, I notice that the molar mass is in the way. I don't have little m all by itself. I need to isolate or rearrange my formula. So to do this, I need to get rid of what is connected to little m on this side. So little m is connected to this variable big M, all right, by the operation division. What's the opposite of division? Well, it's multiplication. So to get rid of big M, I'm going to multiply by big M. All right. When I have little m times big M divided by big M is going to cancel out. But what I do to one side, I need to do to the other. So I'm going to multiply by big M on the other side. Rewriting this, I have that m is by itself, and it's equal to big M times little n. So now I have little m all by itself, and I can sub in. All right, so we sub in our molar mass, 32.00 grams per mole. We're going to multiply by the number of moles we were given, and we're going to math that in our calculator. I get 10.1 grams for our mass. All right, I'm going to leave this last one here for you to try on your own. You could note that the final answer should be, in the end, n is equal to 0.1091 moles. Can you show your work to get there? Don't forget, the post-it notes have all of the work shown. All right, the last thing we're going to do is we're going to turn our number of moles that we calculate in our questions into the number of particles that we are counting. Okay, so sometimes we're counting atoms, sometimes we're counting molecules. So we have a formula that can get us there. The formula is big N is equal to little n times NA. Now, what on earth does this mean? Well, this is moles, and that's the unit MOL. Big N is the number of entities. So like the number of molecules or atoms or whatever it is that we're trying to count. Okay, so for oxygen, it's the number of actual O2 units that we are counting. All right, so what is NA? Well, N little a is Avogadro's number. It's on the back of your periodic table at the very bottom of our formula sheet, all right? And the number is 6.022 times 10 to the 23 per mole. So whatever we're counting, there are 6.022 times 10 to the 23 of them per mole. All right, so let's use that. How many molecules, so counting the actual molecules of O2, are present in 0.05381 moles of oxygen? So we're being asked to find big N, okay? How many molecules or atoms or whatever it is that we're counting. We were given little n, the number of moles. And we have Avogadro's number. It is a constant. It is always known. I don't have to calculate it. I just look it up per mole. So let's sub in here then. So we need our equation. So again, when we're doing math, we always write out the equation first that we're going to sub into. Then we're going to sub in, hopefully in order. So the number of moles, 81, times Avogadro's number. And then we're going to put that in our calculator. How do we do that? Well, we have to use some math here. So put in this number, 0.015381 times 6.022. And you're going to want to use brackets here. So we'll bracket this, 6.022 times 10 to the hat. So 10 times 10 to the hat 23. Okay. Alternatively, and better, we can find a button on our calculator that will replace all of those keystrokes. On some of us, it's EXP. On some calculators, the whole button says times 10 to the, and it might have like a hat, or it might have like a little X here. Or if you have a TI or a graphing calculator, you're going to press the button second, okay, the yellow one on my calculator. And then the button above our 7 is a comma. And it has an EE above. And this, when I say second comma, it puts an E in my calculator. So it says 6.022 E, and I'm gonna write 23. When we do that, it tells our calculator, hey, this is a number in scientific notation, not asking you to do bedmass and order of operations. Please just multiply it. All right, you multiply those out and hopefully you get the same answer that I did. I got 3.240 times 10 to the 23 molecules of oxygen in 0.05381 moles. Okay. Oops, I'm in error. I was like, this doesn't look right, so I recalculated. It should be at times 10 to the 22. So my calculator says 3.24043 E22. And we have to remember that the E means times 10 to the exponent 22. All right, I want you to try it again. All right, our next example is how many atoms, or again, molecules, are present in 0.00205 moles of sulfur. So we have the number of moles. We have Avogadro's number as always. We're going to use the same formula. What I'd like you to do is try it on your own from here, and I will give you the answer. Pause it now. All right, the answer I calculated. All right, the number of atoms I got here was 1.23 times 10 to the 21 atoms present, or molecules of sulfur. Molecules. Because, again, sulfur is S8, so I can't really say atoms when I'm talking about something that comes in molecules. Now, I see one below here. It's about writing outside in chalk. I didn't break the chalk today. Maybe we'll see if we have some time for it next week. But what I would encourage you to do now is go and practice calculating molar mass and calculating mass and, number of moles from mass, or vice versa, calculating the mass from moles using our previous formula. And then if you're feeling pretty good about it, I would encourage you to try this formula. This is less important. The N is equal to little m over big M is really important moving forward in chemistry. Same with calculating molar mass. So I'd really focus my time there to make sure I am good at those calculations first before practicing these ones.